Okay, so welcome to week 7. So basically today we will deal with different topic, which is somehow related still to the what we started. What we started basically, before I continue, how is the sound? Can you hear me clearly?
It's good. It's good. Hydrophobicity.
Very good. So basically, today we will cover the third and the last set of notes dealing with power system component dielectric or electrical insulation testing. We talked about destructive tests, and we said that the criteria for the destructive test either pass or fail. And then we talked about non-destructive tests, which is basically a quality test. We want to see the quality of the insulation. These two lectures were about assets in the lab when you are manufacturing it. So it's still in the manufacturer premises. Did not go to the customer yet. It's not in service yet. But when you install the asset, with time it starts to degrade. And you want to see what is going on there. You want to see the health condition of these assets. How good, how bad are these assets? Do I need to do major maintenance? Do I need to do some replacement? Because the worst thing for me as a utility engineer, when a failure happened in a major components, and I was not ready for it. I was not really planning for this to happen. So I always try to be proactive and do some field tests. So today we'll talk about field tests, and I will concentrate on two assets: transformers and outdoor insulators. I thought instead of being spread and talking about two different assets and without a little bit of depth, I thought maybe I will bring these two assets that I will go a bit of depth. There is some overlap, what I will mention today, and your lectures or your term paper presentations. I will try to add certain things different than what you presented during the term paper. Okay, so let's start. We'll start with transformers. This is the easiest test, simplest test, but it is very, very effective. So this is done as per ASTM D1500. You need just to take a sample from the oil, and usually we can take it from the oil drainage valve. Usually you have one at the bottom of the transformer tank. So you take the sample, and you take the sample in some sort of container that is transparent so they can see inside it and see the color. Now, when you look here to the color of the transformers, this is like good. Okay, as we're going this way, it's getting worse and worse. And you see here clearly that the color start to get more and more darker color. And there is a scale for that from 0.5 to 4 with the steps of 0.5. So 0.5, 1, 1.5 until you reach 4. 4 is very, very dark. 0.5 is very, very light in color, and that as if it's like a new transformer. So by having this, and there's a scale in the industry, they have that scale. By specifying the color, you can get a very good idea about the level of the contamination in the transformer oil. I just forgot to mention that why we are mentioning the transformer oil. Transformer oil, you can think of it as the blood for the human beings. So basically, whenever you go to the doctor and you take a sample from your blood, why? Because it can actually reveal a lot of problems. You can reveal about diabetes, cholesterol, many things in our body can be revealed from them taking a sample of the oil from your blood. You think about the transformer oil with the same way. When you take the sample, all the tests we'll talk about, or most of the tests we'll talk about them, are from the transformer oil, but it reflects the health conditions of the transformer. Now, when you're getting darker and darker, this is an indication that there is a deterioration in the oil, contamination, and maybe also some problems with the transformer insulation paper as well. Second test is the interfacial tension. And this is covered by ASTM D971. Now, it measures the tension of an insulating fluid, which is here in our case, basically this insulating fluid is oil, transformer oil here. Okay, how much this surface tensions against water. Okay. So let's see how we do the test, and then we'll talk about what does it really mean. Okay. So first, it is basically a very good mean to detect any oil-soluble polar contaminants or any oxidation products. So oil-soluble polar contaminants, like for example, water. It's a good way to detect water in the transformer oil, or if there's any oxidation, any chemical reactions, with oxygen. So that will lead to some oxidation of the oil. It's also a very good way to measure that. So basically what you have here, you have a sample. This is water, okay? And carefully you add the oil on top of the water without them mixing together, okay? So you add it and make it floating on top of the water. And then you will have a platinum ring. This is the platinum ring here. This is the platinum ring here. Is here. And you put it below the water level, okay? And then you wanna pull it up and see how much force will be needed so that you can take out this ring, okay? So the force is measured at the point at which the ring break free of the water layer, okay? So now let's understand what does this mean, okay? When the oil and the water are more close to each other, meaning that we have more of polar contaminants, because water is a polar material actually, okay? Then it becomes easier and easier to pull out this platinum ring with a much less force. So this test, the higher the needed force, the better is the oil, meaning that the chemical composition of the water and the oil is completely different, okay? And there is no any contamination in the oil. I want to add here something. This test is considered as very actually difficult test, and it's not easy to conduct and needs some special people with special skills to be able to do that, understand what is going on. And this is why one of the projects I assigned to you is to predict the IFT, the interfacial tension. Why? Because it's a very hard test to do, as you can see here, compared to other tests, as we will see, like for example, water content or breakdown voltage or acidity. These are relatively much easier tests to be done. So if we can predict this value, which is, in my opinion, this is one of the very critical tests in transformer oil, can reveal a lot of things about it. Electrical test, the breakdown test, this is the standard test. And it's done as per the ASTM standard D877. I mean, all the standards I mentioned to you here, there is some counter standards in IEC standard, but I'm just using the ASTM here because this is what is used in North America. Now, that test, basically, you try to see how much withstand voltage the oil can take. So basically, apply a voltage until you have a breakdown, and you want to see what is the strength of the transformer oil, how much voltage it can take. So it's an indication when the transformer oil, of course, obviously, when the breakdown voltage goes down, it reflects. It is a meaning that there is some conductive contaminants, such as water, dirt, moist, or even some cellulose fiber that bridge the gap between the two electrodes and what causes the flash over to happen. So for this test, the higher the breakdown, the better is the transformer oil. However, and this is also from experience, that if you have oil with a high breakdown voltages, that does not mean that the oil is good. And I have seen some samples of oil, very dark in color, means that there is a lot of contaminations and or oxidation happen to the oil, so it's not really a good oil, but still the breakdown voltage is relatively high. So in my opinion, this is one of the least sensitive tests that reflects the quality of the oil, but nevertheless, most of the utility, they have this test because it's an easy test, and it gave them some indication about the strength, because once the oil cannot withstand the voltage, it becomes really bad, and you have to do an action immediately if it reaches to that level. So how the test is done? So basically here it is an automated test. So nowadays you don't need to do it manually. You don't need to do it manually. It is basically, if you see here, this is the cell here, and here is the electrode inside. So basically this is, you remove it, you take it out from here, and you add the oil, you cover the electrode here, okay, and you put it inside this cell. So this is the electrode that you see here is two hemispheres. So this is something like this, two hemispheres, and the distance between them, as mentioned to you here, it is 2.5 millimeter. Now, this is the start button of this test. You start the test. The voltage rise is 2 kV per centimeter. So the test continues until a flashover happens. Now, when the flashover happens, and as usual, this is an oil. It's from mineral oil. It's a hydrocarbon. Some carbon will be released. Okay. Now, one test is not enough to get a value of the breakdown strength. So the test is done actually 6 times. So repeat the test 6 times, and we take the average value. However, if you just repeat the test every time, because of this contaminant, it will reduce the value, not because of the quality of the oil is bad, because now you are introducing a contaminant coming from the test, because we have a flashover. Okay? So what we have here, we have a magnet steering element that after the test is done, it starts to rotate, to circulate the oil, and to dispense this contaminant so that it's not really concentrated in one point that will affect the result. And again, this is done automatically. So you apply the voltage, and the voltage increases until a flashover happens. Then the steering element starts to rotate, circulate the oil. Then basically then you apply the test for the second time, for the third time, until it reaches 6 times, and then you get the average value. So you get here. This is a very standard. I used to have this piece of equipment a long time ago. Even you get here a printout with the 6 results and the average value of these results. Dissipation factor we talked about. And we said that the dissipation factor, it reflects, it's a measure of the resistive part of the current, of the leakage current. If we have a pure capacitor, a pure dielectric material, it is a pure capacitive current. So there's 90-degree phase shift between the voltage and the current. However, we have a small resistive part. Why? Now we understand, because the oil now ages with time, and there are some contaminants, there are some polar and non-polar contaminations, exudations, so fibers. There are many things there which will lead to having some definite resistive current. Small, yes, but it's still there, and we can measure. And the power dissipation, or the dissipation factor, or the power factor, can be measured on the site as well. Tan delta. I'm trying to make a video. I did a video for MEGAR and video for PD measurements. I'm trying to do a video, hopefully next week, about the dissipation factor, and about another video. I will talk about it when I reach to this. Okay. Chemical test. So we have physical, we have electrical, and now we have chemical test. Neutralization number, or sometimes we call the acidity. It's done as per the ASTM standard D974. Now, this is measures of the acidic number. Okay. Now, for the acidic number, the higher the acidic number, the worse is the condition of the transformer oil. So we want this number to be as small as possible. Now, if we measure some acidity in the transformer when it is new, it's not yet aged, this is basically, most of the time, is just residual that coming due to the refinery process. So it's not something to worry about. Okay. However, in service, this neutralization number is a measure of the acidic byproduct of the oxidation of an oil. And as I said before, there are chemical reactions there. It is oil under high voltage, thermal stress, electrical stress, and some arcing happens there inside the transformer oil. So an oxidation will happen, and the higher the neutralization number, that means that you have more and more oxidation happening inside the transformer oil. Water also is measured as per ASTM standard D1533. Okay, and oil can be as a free oil, and if it's free, you can easily see it, or dissolved. And this is the most common form, is the dissolved form, which we cannot see. So we measure the water content as particle per million. This is how we measure the water. And there is the Fisher iteration method. It's a very standard method that is used to measure the water content. Now, and the dissolved water affect the dielectric breakdown, but it is more sensitive test than the dielectric breakdown. Yes, it will. If you have higher water content, then the breakdown definitely will go down. But the water content is one of the very sensitive tests. These are some typical accepted value for aged oil, not new oil. For example, dielectric breakdown, the minimum, this is the minimum value, is 26 kV. That is the minimum voltage. Now, remember this 26 kV applied when you have 2.5 millimeter gap between the two electrodes. Now, for new oil, basically this goes to 60 kiloohm. The interfacial tension, the minimum value is 24. Now, for new oil, it goes, I think, to more than 40. Okay, so that is the accepted value of age. Now, why are talking about age? Because we are talking about here field tests. So that is the typical values you will find in the field. For the water content, the maximum value is 35 particles per million. For the acidity, the maximum allowed value is 0.3. What if it exceeds these limits? What is the action here? Now, as I said, the oil is a reflection of the health condition of the transformer insulating system. So there are different actions can be taken. Sometimes you recycle the oil. Okay, if it is really start to become close to these values, or sometimes you need to change the whole oil and bring new oil. Like as again back to the blood example, you can do some. You can add more blood to the human body. You can take the blood, take out the poisonous material out of it, and sort of filter the blood if there is a lot of poisons residual in the human blood. Same thing we do here for the transformer. Now there are some other tests, but I try to present the most common and the most practical tests that we do in the transformer oil. So these are basically what we call them the physical or samples from the physical, electrical, and chemical tests. Okay. Now we have the dissolved gas analysis, or what we call it for short DGA. And after this, the level of presentation we heard last week, I'm quite sure you guys now become an expert in this area. So I'm trying to go fast here because it's already covered. Now, there is a difference between the DGA and the other tests we mentioned. The other tests, it doesn't really necessarily reflect an existing of fault. It might reflect that there is a fault, but the previous test is basically a measure of the aging process that happened to the oil, the overall aging of the transformer, getting older and older. So this number would start to either increase or decrease, depends what type of parameters we are talking about. But the dissolved gas analysis, it's an indication of a fault happening inside the transformer. The transformer could be a new transformer. The oil, maybe not aged oil. Okay, it's not related to the age of the oil, but it is related to the existing of certain fault happened in the transformer. So basically, again, we take a sample from the oil in a glass vessel, okay, and we go and we try to analyze the gases inside them using some chromatography analysis, gas analysis technique. Now, what does this reflect? As you mentioned here, sometimes you can look to the absolute value. It's not very indicative, okay? But some people look to those values. And recommended guide. This is again for all age transformers. If N is the number of years in surface, okay. So these are the gases we are looking for: H2, CH4, CH4, methane, C2H6, ethane, C2H4, ethylene, C2H2, acetylene, CO and CO2, and the total combustible gases. Okay, so these are sort of some limits. Okay, so for example, for H2, it's 20 N plus 50. N is the number of years in service. Okay, so let's say if you have like 10 years of transformer, so our recommended value less than 20 times 10, which is 200 plus 50. So it should be less than 250 ppm. So again, because now there is no fault in the transformer oil, existing fault, severe fault, then the values can be a relatively small value, and you can tolerate again with the aging, because fault happen in the transformer from time to time. And now when you do the DGA, now yes, there is an online monitoring technique, but before you took a sample, and you took a sample basically every year, every other year. So there might be something happening in between, something not severe when you took the sample. So the residual of those gases can still be there. Now with the online monitoring system and the DGA, things has changed a little bit. Now they know in real time what is happening. And now with the development in communication systems, in the SCADA system, people can see actually what is happening in the station, the substation, or the monitoring station, where you can see in real time for what transformer, what is the dissolved gas analysis. Now these gases, they reflect certain type of problems, like for example, H2 is corona or partial discharge, C2H4 is overheated oil, C2H2 there is arcing habit, and CO when we have overheated cellulose. Okay. Now, as I said, the absolute value may not be the best. So there are some techniques, and one of them is called the Duval triangle. Let's try to understand how the Duval triangle works. So the Duval triangle, basically, you bring the percentage of three gases, which is C2H2, C2H4, and CH4. These are the three gases that you bring. Okay, and basically you try to see their values. So basically you find, for example, you have X, Y, and Z. This is your how much ppm is your CH4. This is your C2H2, and this is your C2H4. Okay, so you find the X, Y, and Z, and then you will find the percentage of, let's say, CH4 by having X divided by X plus Y plus Z times 100. You find the percentage of your C2H2, same thing, which is equal to Y divided by X plus Y plus Z times 100. And finally, the percentage of C2H4, which is equal to Z divided by X plus Y plus Z times 100. Okay, so once you found these, you bring it to this triangle. And you try to see these 3 points, they have to intersect at one single point. If it intersects at more than 1 point, it means that there is an error in the calculation. So they have to intersect at one single point. And then you can see here the triangle is split into 7 different regions. You have the partial discharge, T1 to T3. These are basically our thermal faults. And D1 to DT, these basically are electrical faults. Okay, so you try to see where is this point of intersection happening, and then you can figure out what is the type of the fault that happened inside the transformer. Let's have a specific example here. So, for example, this is some typical lab measurement tests. Okay, and you have the H2, CH4, CTH2, and so on and so forth. As I mentioned, you are interested only in 3 gases: CH4, C2H4, and C2H2. So CH4, C2H2, and C2. These are the three gases you are interested in. You are not interested in anything else, at least in the Duval triangle. There are some other techniques, use other gases, but I'm talking here specifically about the Duval triangle. Then you do the calculations. You find the percentage of, okay, here, I think this is, I think there's a typo here. Should be not H2, this should be, this is CH4, C2H4, this should be C2H2. Okay. So here it is basically, you find the intersection point here. This is your intersection point, and this is your D1. I think that is another form of the, let me confirm this to you guys. Let me check this. I think this is a different way of doing the Duval triangle, but let me go back to my references and confirm this to you. So why they are using H2 here instead of the classical one here? The classical one, they are using these three gases. Okay, so why they are using H2? Let me go and confirm this. We have here the C2H4, and we have the CH4, but then we have the hydrogen here instead of the C2H2, acetylene. Okay, so let me go and check this point. Okay, now the acetylene here is 616. Okay, 616. Basically, you will see it is somehow, it is, even if you take instead of the H2 and have this is as your C2H4, basically, you will find that it is somehow, it will be very, very close to this as well. Okay, but I will check and come back to you. I might send an email to correct this, or I will change the slides. Okay, so whatever. Anyway, so let's go back here. So the point of intersection here that you see here is basically the point that reflects the where is the intersection. It has to be in one point. So this is in D1. If you go back here, D1 is basically a low energy discharge sparking that happened in the transformer. Okay, so that is how we can use the Duval triangle. The last test I talk about is the SFRA, the sweep frequency response analysis. Again, many of you present that, so I try to measure, try to present something different. But the test, in simple way, you apply a variable frequency input signal, okay, that goes from 20 hertz to 2 megahertz. Then you measure the response. So maybe you apply from the high voltage response in the high voltage while keeping the low voltage open or short circuited, or apply to the low voltage, measure in the low voltage, and so on and so forth. So now you will have here basically the applied signal, and you will have the measured signal. And from this, you will generate two graphs, the magnitude of your response and the phase difference between the input. So this is the phase difference between what you apply and what you basically receive. Okay, and basically you get the phase. Okay, most of the things or the information are available in the magnitude. So what does it mean of this graph that you generate the magnitude? It can be divided into 4 regions. The lowest frequency region, this is dominated by the core, meaning that if there is a defect in the core, basically you will see some discrepancy happen in that region. In the middle here, in the frequency region, that there is a problem between the windings. Okay, so that reflects the interaction between the low voltage with the high voltage windings, low voltage with the tertiary winding, and so on and so forth. Then a bit higher here, this is the winding structure within themselves. So if there is an issue within the high voltage winding or the low voltage winding, it can be reflected in that region. Finally, the last highest region, this is basically from the setup and the lead connections. Okay, now why we use the SFRA? Now the SFRA, first you have to have a signature. Okay, so when the transformer is manufactured at the factory, you have a fingerprint. Okay, so you keep that fingerprint for you. Okay, and then you use that fingerprint to compare it when you do the scan for the transformer at a different condition. So it could be, for example, after transportation, when you transport the transformer from point A to point B, the vibration, the movement, something, especially the core might be moving, then you need to take another signature, okay? And that if they are matching, then there is no issue. If they are matching, then you will know where something happened inside the transformer. Also, to check the in-service of the transformer. If a fault happened inside the transformer, you start to have a short circuit within basically the windings. If there is start to have a deformation in the windings, then all of this can be detected in service, okay, using the SFRA. And finally, if an earthquake happens in a certain region and you want to see if the transformer internally something happened to it. Okay? But this is always rely on the fact that you have to have a fingerprint. Now, sometimes if you have a similar unit, you might use this as a fingerprint if you don't have actually any other fingerprint for the actual transformer. However, this test you have to be very, very careful when interpret the data. Okay? Because you can easily misread the data and come up with certain wrong conclusion. I will give you just two examples here. The first example here, when you look here, this is the SFRA for the three phases. And one of you, if I recall, mentioned that the middle phase has a different, basically, signature than the red and the blue. Now, the red, yellow, blue, it is exactly, it's the A, B, C phases, or the U, V, W. This is how the European, this is how the here in North America, this is the IEC, sometimes British standard, red, yellow, blue. So we have different ways of calling the phases, but this is the middle phase. So the middle phase here, you see here, coming here in the core area, this is all low frequency. Low frequency means in the core area, there is a discrepancy. Why is that? It's very simple. If you look to the structure of the transformer, this is the middle phase. This is the phase yellow or phase V or phase B, okay? You see here now, when you energize the transformer, this is the core path. It will go, the flux will go here and will go there, okay? Now for the other two phases, the core seen by the winding is different. But for the right or the left, you see, this is one path of the flux, and this is the other path. It's longer path of magnetic material. So the core seen by the winding is different. And this is why the two extreme phases, they see the same amount of core as opposed to the middle phase. And this is why they have difference. So this is not because there is a defect, but this is because of the natural design of the core type transformer. So this is something you have to watch. Another issue, also, when you do the fingerprint of your transformer, you have to make sure that what was the connection of the transformer. Very, very important. For example, here, we are taking the signature for the applying to the high voltage, and we're receiving it from the neutral. Okay, so that is our system. Here we have the low voltage open circuit, and we have the tertiary winding short circuited. Now, if I come and I forgot this condition, and I will just open circuit the tertiary windings, you will see here a huge difference happened between what? This is the middle region, interaction between the windings. Now, because I changed the connection of the winding, there's a huge difference between the two. So if you don't know exactly the condition at which you have done the test, this will give you some misleading results. Okay, so you have to know for sure what was the connections when you did your SFRA, because it seems that sometimes there are different ways of doing the SFRA. So you have to, it's not just enough to have the SFRA signature, but also you have to know what is the conditions for that. Okay, so that's for the transformers. Any questions so far? Good. So we will have a little bit of outdoor, and then we'll have a break. Okay. Now, what are the field tests that we do for the outdoor insulators? One of the test we do in the site is the hydrophobicity assessment. We said that we have polymer insulators and we have ceramic insulators, and we'll talk about that in details in the coming week, the difference between the two. But one of the properties of the polymer insulators is their surface is hydrophobic when they are new. Hydrophobic in the sense that when you have a wetting on the surface, the water basically will be like a small droplets, discrete droplets, not connected to each other. And this will prevent any development of a current on the insulator surface. But as the insulator age with time, this property is gradually lost. And you can see here, you can start until we reach here, we have here almost complete wetting. Okay. And that's an indication that the insulator is basically lost its that important hydrophobicity property. So how we do the test basically, how we can classify. Now, this was basically a technique that was invented by the Swedish Transmission Research Institute, STRI. They came up with this technique, but now the IEC standard adapt this technique and they make it as have a guide for that. So basically, you go to the site, you spray water on the insulator. The sprayer has certain specification, the distance has certain specification, and then you take an image, okay? And then you based on the guide, these pictures coming from the guide. You look to the pictures and you try yourself. You try to find the image that you have belong to which class. So class 1 and 2, you can see they are excellent. 3 and 4, they are moderate, but 5, 6, of course, 7 when it is completely wet. These are bad, bad insulators. Now, people try to automate this nowadays. This is one of the research areas that I'm really interested in, is to use deep learning, machine learning, and trying to have this automated. So you don't have, let's say you don't have an expert who can look into those samples and can judge them. We're trying now to do this on a mobile app, so that you go there, you take the picture in the site, and you right away you get that classified, and it will tell you what is basically the classification or the class of the hydrophobicity. So that is one of the techniques that we use it for non-ceramic insulators. Also, we use the IR. Now, whenever there is an increase in the temperature, there is basically a radiation of spectrum called the infrared. And this can be detected by using a sensor. It's basically a photodiode. And that diode can analyze this type of spectrum, and we can show it to you. So here, this is a non-ceramic insulators, and you can have here a localized increase in the temperature. This is most likely basically an indication of an internal fault. Now, because those insulators, and again, I will mention that in details next week, basically you have a fiberglass core, and then you have a mold. On top of it, you have the silicone rubber molded on top of the insulator. Sometimes the mold, there is not good bonding between the rubber and the fiberglass core, okay? And this maybe can be detected at the manufacturing premises, but as transformer age with time, as there's enhancement in the electric field, because it's some air void there, some partial discharge, and then some tracking start to happen, then you start to have an internal arcing, which will significantly increase the temperature until maybe a complete failure happen in the insulators. So the IR camera can be used basically here to detect there is internal tracking. Also, if there is external discharge, dry band arcing, also it can be detected using the IR camera. Another technique, which called the buzz technique. In the buzz technique, that is basically the insulators are energized. Okay, so let's say we have here the high voltage here, and here we have the ground. Now, this is a conductor, and this is a conductor. This is called cap and pin insulator, and in between, this could be ceramic, could be glass insulators. Okay, now, so this is conductor, this is conductor. So This you can look to it as a capacitor. So this is like a capacitor connected in series with another capacitor, in series with another capacitor, in series with the high voltage. So like 4 capacitors in series. Now, when you apply the high voltage, because they are in series, there will be like the voltage distribution, more or less. Let's assume it is you have a similar voltage. There will be a slight difference, but assume you have here V, 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 and V. So every one of those insulators, they have this, they are holding this voltage V. So you bring this detector, we call it the buzz. We'll know why the buzz here. This buzz, basically, you connect it between the cab and the cab of the other insulator. Basically, you are connected across the voltage that is developed across the ceramic insulator. So if this insulator is holding that voltage, so you'll have a potential difference V between this point and that point. There is a voltage V, okay? And this potential difference, it will be between these 2 points. So we adjust the distance between 2 sharp points so that when we have this V, an arc will happen here. So when you have an arc, you hear a buzz sound. You hear a buzz sound, it means that this is a healthy insulator. Now let's imagine the other way around. If there is an internal defect, okay? So this insulator here, internally, there is a defect. It's like a short circuit internally that you cannot see. So if there is an internal defect here, this insulator will not hold the voltage. It will be like a short circuit. There is no voltage there because this is like a short circuit, okay? And the voltage now, instead of being distributed among 4 disks, it will be distributed among 3 disks only. So each disk will have a slightly higher voltage. Now, when you bring your device here across that insulator that has 0 voltage, there will be no buzz, no sound. You will not hear anything because there's no potential difference between these two points, okay? So that is what we call the buzz method. So the buzz method basically doesn't give you the exact voltage across, but it gives you by sound an indication that this disk most probably is internally defective. Or you can measure the voltage. Okay, so here this is measure the electric field along the insulator string. Why that? Again, the insulator is basically energized. So you go and you measure the voltage starting from the high voltage, and you go and using the stick, you measure the voltage until the end. And then you draw the voltage basically as versus the insulator number. We have minus, so here we have 32. So you draw the electrical field versus the number of string. You will find that whenever there is a defective insulators, the electric field will drop. Okay, drop. Why? Because there's an internal short circuit. Could be partial, could be complete. Okay, so whenever there is, so that is a good string. This one is a good string. You see here, the field is somehow uniform. There is no dipping, so there is no any damages in the insulators. But you look here, there is some dipping happening at these points. Okay, so I will stop here for a short break. Can you hear me clearly, everyone?
Yes.
Okay, perfect. Okay, so the last topic I would like to cover today is the partial discharge. Partial discharge is extremely important diagnostic, and as we have seen the week before last week, that it is used in the lab, and it is basically giving you some sort of quantitative number about the quality of the insulation. And in some power system assets, it's a routine test, and some of them is a special test. Now, in the site, as the assets start to age with time, start to develop defects. And these defects can basically generate different forms or different types of partial discharges. And we see forms here because forms in terms of the physical phenomena that is associated with the partial discharge. So whenever there is a partial discharge, different phenomena comes along with it simultaneously. and hence you can use different types of sensors to be able to detect them. So let's say that you have here a high voltage. This is very simplistic example, and here I have some sort of sample, and here I have my ground. So let's say that you have a partial discharge internally or externally. A discharge happened here, but not a fault, but a partial discharge. So whenever there is a discharge happened, there will be a current, a high frequency current going to the ground. So I can detect it if I have a proper current transformer. I can detect that current. Whenever there is a partial discharge happening as well, it will release electromagnetic waves. Okay, so if I have an antenna here, then I can detect that radiation. Also comes with the partial discharge, sounds come with it in the ultrasonic, especially in the ultrasonic regime, which is from 20 kilohertz and higher than that. Then if I have an ultrasound or ultrasonic sensor, then I can detect that. Okay, so these two techniques, we call them like radiation-based techniques to detect a radiation coming from electromagnetics or sound waves. But also there is another category of sensors coming from the basically the radiation, not the visible, or for using vision-based sensor like cameras. Okay, so if you have a discharge, but not internally, but it has to be externally, there will be a UV emitted out of it. So if I have a UV sensor somewhere, then I can detect that partial discharge. So as you can see here, when partial discharge happen, because you have different types of physical phenomena comes along with it, then if you use the right sensor, then you can detect these partial discharges. Now, what we'll see, we'll go through some of those sensors in more details, their design parameters, their pros, their cons, limitations, and so on and so forth. So we'll start with the inductive detection of partial discharge, as I mentioned here, because there will be a partial discharge high frequency pulses going to the ground. Then if I have this inductive sensor, because the coupling between the discharge that goes to the ground and the sensor happen inductively, meaning that the current will generate a magnetic field around it. So if you have the inductive or the current transformer, then you can detect that. Now, you don't, the current transformer here, it has to be designed for this. It has to be a high frequency current transformer, not a regular current transformer, because regular current transformer can measure frequencies up to only 300 hertz. After that, the material saturates. So the classical ferromagnetic material can only measure currents or voltages in that small frequency. But after that, it cannot. And why it cannot? In a very simple way. If you look to the microscopic structure of these ferromagnetic materials, they are made from domains. Okay, so these are some domains randomly distributed. Now, when you are having here a coil and you apply a voltage here, basically, you have a current. This current basically will align these dipoles during the sinusoidal. Okay, so those dipoles will be aligned, positive cycle, negative cycle, keep on changing their basically orientation with the positive and the negative cycle. Now, if you have a very, very high frequency, then there is not enough time for those dipoles to basically rotate. So there will be no induction. So it cannot be used for a very high frequency. Then you have to use a special type of materials that can deal with this high frequency. This is why when you buy those current transformers, you have to make sure that you buy the high frequency current transformers. Now, as you can see here, it's just put it here in the ground. Okay, so it's not intrusive, meaning that you don't need to interrupt anything. Just you need access to the ground point and you have your current transformer there. This is a typical signal This is something I measured myself long time ago. We have a high frequency current transformer, and this is the frequency content of it. So it is 100 of megahertz. It's a very high frequency. So this is around here 0.5 times 10 to the power 8. So this is around 500 megahertz, the cutoff frequency almost. So it's a very, very high frequency. Now, what are the advantages? It's non-intrusive. Non-intrusive meaning that you don't need to interrupt the power. You just need access to the ground. Okay, so that is something very important, especially in the field. In the field, if you want to measure the partial discharge, the technique has to be non-intrusive. Because if it is intrusive, then you have to take the unit from out of service, power interruption. This is a lot of problems, and that's not easy to be coordinated. Also, it can be portable if you have it in a clamp. So sometimes the CTs comes in a clamp, so you can go and connect it to multiple type of connection points. Okay, if you want to go and scan different transformers, you just with the clamp you take over there and put it there and keep monitoring, then move it to the second one, and so on and so forth. So that is another advantage, that you can monitor multiple units, not at the same time, which is one of the limitations. Or it's not easy to be done. You have physically to go and remove the current transformer, and you have connected to something else. Here, there's no external voltage applied. When we talked about the classical techniques, you have to apply an external high voltage. But this one, when the system is energized, you can do that. It's very sensitive. This is one of the most sensitive techniques. A very, very small partial discharge can actually be detected. There is some certain disadvantage, poor direction. You can't find the direction. You know that there is, or can be used also for localization. You know there is a partial discharge inside the transformer, but from where it comes, coming from the core, from the winding, which phase, you cannot tell. And you have to have a direct access to the ground. Sometimes you don't have access to the ground. It's not easy, so you cannot implement this. The last disadvantage, it has a very low signal to noise ratio. What does this mean? It means that when you, this is inductive, okay, so it would detect a lot of noise with it as well. Okay, so when something has low signal to noise ratio, it means that the signal will be highly corrupted with noise. And let's have an example. This is an example of a partial discharge that we measured here at the high voltage lab. So you see, when you look at that signal here, basically, you don't know if that is actually a signal or this is actually a noise, okay? Unless you do some denoising techniques, and this is what happened here, and you can see here clearly the bulbs coming out of it. So that is clearly a partial discharge. But to do that, you need to use, we used here very sophisticated techniques called wavelet transform to be able to extract the signal from the noise. Why? Because the signal to noise ratio is extremely low. So that is one of the disadvantage of the inductive. Now, to help improve a little bit, especially when we use it in rotating machines, we use a coupling capacitor. Okay, so these are coupling capacitors here. You put them in the way between the leads and the current transformers there. And why is that? You want to block the 60-50 hertz components, okay? And only you want to keep the high frequency. So instead of directly connecting it, you use those coupling capacitors to filter out the 50-60 hertz and keeping the high frequency when it is very high frequency, okay? Then it acts like a short circuit. It's a low frequency, it acts like an open circuit. So it will block the low frequency and it will pass the high frequency components. Second way, as I mentioned, the RF. RF stands for radio frequency, detection of the partial discharge. Okay. Now, as I said, here you will have a radiated electromagnetic waves. So if you have an antenna, it can detect that type of radiation. Now, it can be used for internal devices like or PD inside a device like a transformer or GIS, or you can use it also for substation monitoring. Okay. Now, if you use it for an equipment monitoring, okay, you need to have the antenna inside the device. You cannot have the antenna outside the transformer because the transformer tank will shield any electromagnetic waves from inside. Acts like a Faraday cage. So you have to basically insert the antenna inside the transformer. Okay, so basically here you can see this is a transformer. So we are pre-inserting those antennas inside the transformer. Now for new transformers, what we do, we open basically in the tank of the transformer a dielectric window. And so it's a huge tank, and part of the tank you will have dielectric window, and you attach the antenna there. Now because it's dielectric, the electromagnetic waves can reach to the antenna at that specific location. Now, when you have also multiple of those antenna, you will receive signals. For example, this is the source of the PD, so it will travel different paths. So the arrival of the signal basically will not be the same at all sensor, which can help you to localize the partial discharge. So when you have access, and I said that is only you have those antenna pre-installed in the transformer, and this is only happening on new transformers. All transformer, you don't have this luxury to have multiple sensors. So if you have those multiple sensors, you can use that to basically try to localize the region of the transformer. Now, if you don't have access, still there is an access point, which is the drain valve. So you can basically insert the antenna, and you have to modify the drain valve, remove it, and this is the antenna here installed inside. Now, that is basically good. You have an antenna here inside. However, you don't have the multiple antenna, so that you will not be able to localize the partial discharge. You can tell if there is partial discharge or if there is no partial discharge, but you cannot basically localize it. Also, you can use the RF antenna to detect partial discharge in open space, like in a substation. So if you have a surface discharge due to contamination like this one, or corona due to the hardware like this one, then it will emit the radio frequency, and then having the antenna there, it will detect those radiations, and it will tell you that there is a partial discharge happening somewhere in the substation. And because of the directivity of the antenna, you can use antenna directive antenna, meaning that if you basically move the position of the antenna from the source of the PD, you will not detect anything, but it only detects when the antenna is directly facing the defect. So you can localize the place where you can have the source of the partial discharge. The frequency range we are talking about here from few hundred megahertz to few gigahertz. And that will put on the cost, because to measure this high frequency signals, you need an expensive equipment. So the oscilloscope that we use, their price is proportional on the frequency. If you bring an oscilloscope to measure signals in the 100 megahertz, is different than 10 gigahertz, is different than 100 gigahertz. The higher the frequency, the more expensive is the equipment. So that's put some sort of limitations on the RF antenna. So advantages, it's very safe method. You don't need to go closer to the basically the equipment. You don't need to come closer to the ground and connect something. It's completely safe, far away from the source of partial discharge. You have your antenna. There is no direct connection, so it's a very safe method. Also can be used to localize the partial discharge, as I said, having a directional antenna, and by pointing towards the possible locations, you can pinpoint the location of the partial discharge. This is non-intrusive completely, and unintrusive, especially if it is outside the equipment. But if it's inside, like the antenna I mentioned to you, then it becomes an intrusive test. Disadvantages, this is one of the major disadvantages of the RF antenna. It's an antenna. So it will detect any electromagnetic waves, which is bad because sometimes you detect something, you think there is a partial discharge, but it's not a partial discharge. Basically, it is a noise coming from a source of electromagnetic waves. Okay, so you have to have some either experience about the nature of the partial discharge, or you have to have a denoising techniques to remove those noises from the measured signals. Of course, it needs line of sight. If there's an obstacle between you and the object, it can detect anything. And this is why I said if you are outside the transformer tank and there is a partial discharge inside the transformer tank, you won't be able to measure it if your antenna is outside the transformer. It has to be inside. There has to be a line of sight between the antenna and the source of the partial discharge. It suffers from high attenuation, especially if your antenna is far away from the PED source. By the time it reaches you, it might be very small to be actually measured. UV detection of partial discharge. Now, as PD happens, as I mentioned, there will be a radiation of light in the UV range, in the visible range, in the infrared. Most relative spectrum for us at the PD level is the ultraviolet UV spectrum. Okay, and this gives you some sort of feelings about the energy level, how much the intensity of the light, UV light. It gives you an indication about the level of the partial discharge, and basically that is of course a very relative perspective. It can only be used for external because you have to have a visible light coming, UV light coming out of it. So if it is the partial discharge is inside, like for example, if the source of partial discharge is inside the transformer or inside the insulation, the defects, you won't be able to measure anything out of it. Now you could usually we use it, or you used to use it in the night actually. But nowadays, there is also decor camera that you can measure the corona or the partial discharge during the day. So for example, here, this is the night vision. You might have seen that in movies. So you see that this is the night vision. You see everything greenish color. Okay. So, and then here you see those spots. These are basically the partial discharges. These are some partial discharges happened here. Okay, so this is how you can do it. So basically, this is like a light amplifier. So it amplifies the lights. Now the lights, there is no light that is, there's no dark, 100% dark. There is a slight light there. So these cameras basically they try to magnify that light to make it you can see it. But nowadays, and this is a limitation because this is you can do only in the night. In the night, meaning that you have to send the worker with an overtime. But now with the deep corona cameras, you can see here partial discharge clearly during the daytime, so you don't need to use that. But as you will see here, it's very expensive camera. The advantages: there's no direct connection. It's you do it in the service, regular inspection. You can see that. This is one of the best technique for localization because you can see in the RF antenna. Yes, it will tell you that there is a defect in that direction here, but where is it exactly? You don't know exactly. But with the UV camera, you can see the defect yourself, of course, if it is external. It has a very good location accuracy, safe, of course, very safe method. Now, it has certain disadvantages as well. It can only be used for external discharges. So, for example, if there's an internal defect of the ceramic insulators or the polymer insulators, you won't be able to see anything. It has to be something external so that you can see it. So this is a limitation of it. As I mentioned, this is one of the most expensive. The camera is few tens of thousands of dollars, 30, 40,000 if you want to get a good decor camera. So it's relatively expensive. Of course, also you have to have a line of sight. If there's an obstacle, of course, you won't be able to see anything there. And you can only see if there is a fault happening right now. This is same like the RF antenna also, or the CT. All these techniques, you have to have the fault happening right now to be able to detect it. The only way you can detect the fault after it happens, and if you are not physically there, is through the DGA, the dissolved gas analysis with the hydrogen. Hydrogen is an indication of partial discharge inside the transformer. So if you take the sample after a few days, still H2 is there. So you know that at some time there was some sort of partial discharge. Now, this technique and the other technique has no calibration. Okay, so you don't actually measure the quantity of the partial discharge. It is all relative speaking. This is unlike the classical method we mentioned 2 weeks ago. That one will give you the partial discharge as a picocoulomb, so it's calibrated. Okay, although it does not give you 100% the amount of discharge inside the assets. Okay, but it's called apparent charge. It gives you some numbers. But here, all the techniques I will mention today, they are except for basically the inductive one. The inductive one is you are measuring the actual signal. Okay? And even if you take the integration of that signal, you get the charge. So that technique, the inductive technique, is good in that regard. Finally, the ultrasonic, we mentioned also there is an ultrasonic waves are produced. Okay, so every discharge comes up with a sound. Now, some sensors called acoustic emission sensors. Okay, so it could be in the heard region, not in the ultrasonic, but the regular region. Some sensor does that. Okay, but to measure a discharge from the 20 hertz to 20 kilohertz, that is the range of frequencies that we can hear. It has to be very intense. But from our experience, when you use the ultrasonic sensor, which is higher than the 20 kilohertz, even if you can't hear anything, because that is the sound that, I mean, we can't hear it. So the partial discharge could be small in quantity, but it's producing some sort of discharges in that regime of frequencies, and the sensor can efficiently detect it. Now, the speed, this is something important. It depends on the medium if you want to use it to localize. So if it's air, it's different than oil. It's aged oil, different than new oil. So the speed of propagation is basically different depending on the medium. Now, we use here two different types of sensors to detect ultrasonic, either microphones or piezoelectric sensors. Now, the microphone, we use them whenever the partial discharge, we call it airborne. Okay, if it is airborne, meaning the discharge happened in air, like for example, if you want to go and detect partial discharge coming from the hardware in a substation, okay, so that's happening in air, and between the sensor and the source of the effect is only air. Okay, so we use microphones, and microphones working either in the acoustic or the hearable range or the ultrasonic. There is another category, or the other sensors also basically work on the ultrasonic, is the piezoelectric sensor. The piezoelectric sensor is a class of material that whenever you apply a mechanical force on it, it produces a voltage. Okay, it's called piezoelectric material. Now, those sensors cannot be used to detect partial discharge from airborne. This has to be inside a tank. Okay, so if, for example, if this is a transformer and there is a source of discharge here, then you will have waves of oil go and hit the tank. So we attach the piezoelectric sensor here. They are very, very sensitive. So whenever, and because of the partial discharge, those waves hit the tank, there will be some vibration of those sensors, and this will produce sort of an ultrasonic wave in the form of a voltage. So you go and you detect it, and this is how you can use it. So this is the piezoelectric. If you have transformer, GIS system as well, anything enclosed in a tank, then you have to use a piezoelectric sensor. Anything airborne, then we use the microphones. Now, an advantage here that the range of frequencies is little. It's smaller, much smaller than the acoustic emission. And the reason for, the advantage of this, then the data acquisition system doesn't have to be expensive. because I'm dealing now instead of giga or 100 of megahertz, I'm dealing with kilohertz. So the acquisition system becomes extremely less expensive compared to the RF. So this is how, for example, this is in the transformer. We have here the sensor connected here, attached to the now signal conditioning. You might need an amplifier. You might need a filter, okay, to get the signal here, and then it will go to your data acquisition. Or this is an airborne type of sensor. Now this an ultrasonic. You see here, these headphones basically that you can change those signals from the ultrasound to something that you can hear. You can play with the frequency. One way to do that, this is the, let's say, the ultrasonic signal, okay? It's a very high frequency. If you take the envelope of the signal, detect the envelope only. So you can put, and this is the only, so you pass this through a low pass, you take only the envelope detection. There is a technique for that, and then you can have a low pass filter to get rid of the high frequency components. Now this is a low frequency component that you can hear it. So by just having the envelope of the ultrasonic signal here and the processing happen inside the device, then you can listen and you can hear something coming out of this. So this is why we use those headphones. This is a typical partial discharge signal coming from a transformer structure. This is using the piezoelectric sensor. This is something that we did sometimes measured, and here the frequency component, and you can see here the frequency content is basically in kilohertz, basically. So this is like 20 kilohertz, 40 kilohertz. So it is very small compared to the RF antenna. So the advantages, there is no connection of high voltage. Again, this is an online detection of partial discharge. Easy inspection and safe detection as well. Okay. Now, because this is, you are measuring here sound, okay, then it is not interfered with electromagnetic radiation. We mentioned in the RF antenna that it can detect any electromagnetic radiation, and nowadays you have a lot of electromagnetic radiation. This is immune from that. Now, someone say that, okay, but we have a lot of mechanical noise around us. This is why you use the ultrasonic. In the ultrasonic range, it will measure only the sound that we cannot hear coming out of the source of the partial discharge. Also, like the basically the RF antenna, it can be used to localize the partial discharge source using multiple sensors. So if we have multiple sensors, and personally I have done that several times to localize the partial discharge inside the transformer, and it is very effective. And here one big advantage of the acoustic compared to the RF, we mentioned if I want to have multiple RF sensors, I have to have the pre-arrangement in the transformer tank. Okay, because I can't insert multiple RF antenna if it's not pre-exist. But the acoustic, no, you don't need to do that. In the acoustic, basically, because they come up as a piezoelectric material, you attach it to the tank, and usually there is a magnet to hold it. Okay, and you can take it or you can add it. So basically, the system can be used to inspect a transformer, having multiple sensors at different locations, measure the signals if there is any, and try to localize the partial discharge. And it's very good in that aspect, and it's not intrusive completely. Okay, as I mentioned, it's not sensitive to any electrical discharges. It is only sensitive to the ultrasonic, so it has much small false alarms coming out of it. Disadvantages, again, there is no calibration. You are measuring a signal, okay? But you don't know the source. What is the actual partial discharge? Why is that? Because imagine if you have the same source of partial discharge and you have a bit different distances. You measure it at one time at X and then measure it at Y, you will have two different signals. So distance is basically will impact the magnitude what you measure. Also, it depends on the medium between you and the sensor. It depends on the location of the partial discharge Is it within, inside the insulation, outside the insulation? So basically, it is good to detect there is partial discharge, but you cannot really calibrate that and say, okay, it's a high level or a low level. Again, it needs line of sight, and most of the sensors we mentioned today, they require also line of sight. Now, the signal here is very weak, and it needs a preamplifier. But now devices, I have one sensor, it has ultrasonic phone, microphone, and it has everything inside. The ultrasonic sensor cost is around $14,000. So it's very effectively to detect any partial discharge in an external system. That's not good for transformer. I used to have piezoelectric sensor for transformers as well, but those ones are not good for airborne discharges. So each one has its own applications. So that's for today. I will stop the recording.